This is part 2 of lesson 10.9, using power series to write functions. So we're going to start with example 4, which is find a Maclaurin polynomial for f of x equals 1 over x squared. And in part A, we're going to break this down, and we're going to first find the first 4 non-zero terms, and then a general term. Now, the reason why we're calling it a Maclaurin polynomial is because we want to recall that that means that it's centered at 0. So we don't have to adjust our x term like we did in example 3 here, where we had to, I have it here in purple, you had to change x to x minus 2. So we can leave x alone. Okay, so how we're going to start this is we are going to just write it out, make it look like a geometric series, and use the geometric series form of an infinite series to write this. So let me just write that up there. So we want it in this form, 1 over 1 minus r, so that we can, because that's the sum, we can use this series hang on, I'm having trouble with my pen again. That series where remember that the absolute value of x has to be less than 1. That we can use, whoops, let me try this again. So we want it in the form of our geometric series, which our sum looks like this. So we can write the infinite series this way. And remember that the absolute value of x has to be less than 1. So that's the whole goal. Okay, so starting out with the first 4 terms, the first thing we want to do is we want to make it look like our 1 over 1 minus r. So we're going to take 1 over 1 plus x squared, and we're going to write it this way. We're going to change that plus to a minus, and then we're going to put the negative x squared in parentheses, so that it still is x squared, positive 1 plus x squared, but now it looks like it's in the form of a geometric series. So what this gives us then is we have an a of 1, and our r is now going to be negative x squared. So now we can write the terms. So they look like this now. Our geometric series is going to be n equals 0 to infinity of negative x squared to the n, and writing that a little nicer so it's cleaned up a little bit, we have this alternating series, so we can pull our negative out, and then we have x to the 2n power. So now we can write out the 4 terms. We have our general term there already. So this is going to be 1 minus x squared plus x to the 4th minus x to the 6th, and so on, like that. Okay, now we're going to find the interval convergence. So what we need to do is, let's go back and just review how we find intervals of convergence instead of jumping ahead and knowing we're going to end up with negative 1 to 1. So let's use our ratio test here. This is a review. So we're going to do the limit as n approaches infinity of the absolute value of the n plus 1 term over the nth term. And we're going to simplify this. So we get the limit as n approaches infinity of, simplifying this, we're just going to be left with the absolute value of x squared, which isn't affected by n at all. There's no n in that, so it's just going to be the absolute value of x squared. And so remember, this converges when the absolute value of x squared is less than 1. So that leads us to the idea that we have negative 1 is less than x, which is less than 1. We have to check the endpoints. So we're going to check when x equals 1. So when we do that, we have this series, n equals 0 to infinity of negative 1 to the n. And then we just have another negative 1, since that should be a negative 1, since that's what our x is. Negative 1 to the 2n. So simplifying this, we get negative 1 times to the n times a negative, just a positive 1, because it's always going to be a positive. So this is going to diverge, because it's just going to be negative 1, positive 1, negative 1, positive 1. So this diverges. And then we're going to check at x equals positive 1. And we're going to have this series. So we're going to have our negative 1 to the n. And then we're going to have the exact same thing, because we're going to have positive 1 to the 2n. So that also diverges, because we're going to get negative 1, positive 1. So our interval of convergence is just going to be this. It's not going to be good at the endpoints. Okay, so now we're supposed to use our calculator to compare the original function to the first 5 terms of the series in part A. And what do you notice on the interval from x equals 1/2 to x equals 2? So I went ahead and I put those two in the calculator, and I just have the first 4 terms. So we're just going to let it go with that. And when I look at my graph, it looks like this. The blue curve is the original function, and the red is my power function. So from 1/2 to 2, we can see that they start to diverge away from each other. If we look at the table, what we see is starting from 1/2, they're very close. The function itself in blue is 0.8, and our polynomial is at 0.7969. And then at 1, they're already starting to pull apart. We're at 0.5 for the real function and 0 for our approximation. And then you can see from 1.5 to 2, there's a huge gap in the values between the actual function and our polynomial. So what we can say here is that on the interval, of x equals 1/2 to x equals 2, the Maclaurin polynomial decreases rapidly and no longer compares closely to f of x, which is what we'd expect, because remember, our interval of convergence is only from -1 to 1. So if we look at that table again, we can see from -1 to 1 is really the only space where they are somewhat close to each other, and it doesn't include the endpoints because we're already half off at -1 and at 1. But in between, those values are very close. That's why that interval of convergence is very important. So this problem is a nice connection between what we did in the last section and our Taylor polynomials, plus what we're doing now by writing power series in terms of geometric series. Okay, next example. It says, Given f of x equals cosine squared, use substitution in a known power series. So we're first going to find the Maclaurin series for f of x. We're going to give the first 4 non-zero terms and the general term. Now let's remember from what we did with our Taylor polynomials that the Maclaurin approximation for cosine, if you want to look back at that, is cosine of x can be approximated by 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So if we want to square cosine, we're just going to square all the x's. We're not squaring cosine, I'm sorry, we're squaring the x. So we're going to have cosine of x squared is going to be approximately equal to 1 minus, and now we're going to have x squared over 2 factorial plus x squared to the 4th over 4 factorial minus x squared to the 6th over 6 factorial, and so on. So if we simplify this and make it look really nice, we're going to have 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 3 factorial, and moving on. This will give us a general term, I'll write more dots here, of our -1 to the n, and then we're going to have x to the 4n, and that's all over 2n factorial. So there's our answer right here. Okay, part B says use your answer to find a Maclaurin series for the derivative. So we're just going to take the derivative of our new power series and then write a general term for it. So f prime of x is going to be approximately equal to derivative of 1 is 0. The next derivative is going to be -4 x to the 3rd over 2 factorial. And this is why we like power series, because we can just use the power rule, plus 8 x to the 7th over 4 factorial minus 12 x to the 11th over 3 factorial, which is a lot easier to, whoops, I made a mistake there. This should be 6 factorial here. Apologize for that, because I'm looking at that and I realized that that didn't make sense, over 6 factorial. So anyway, what I was saying is it's a lot easier to use a power rule. We just have variable to a positive integer times some number, which is great, a rational number. So this is going to lead me to a general term. It's still alternating, so I have -1 to the n, and now I have 4n times x to the 4n minus 1 all over 2n factorial, just using the power rule on my general term here. That's all I did. Brought the power down right here, lowered the power by 1. The rest of it is all constant, really. Okay, next problem, example 6. Given f of x equals arctangent of x centered at x equals 0, find a power series representation for f of x known as Gregory's series. So he obviously was a mathematician that studied this. So this is kind of tricky, and it's kind of cool how they figured this out. What we want to start with in this case is we want to start with the derivative of the tangent, or arctangent. So we know that f prime of x, which would be the derivative of arctangent, is 1 over 1 plus x squared. So what we want to do is represent that as a power series and then integrate it. So we'll do that, and we can integrate it in 2 ways. We can integrate it right from the summation, and we can also integrate it from writing the terms out and finding a general rule that way, because we're really just going to be doing the power rule in reverse. So we want to remember that we can think of this as 1 over 1 minus negative x squared, which is what we did in example 4. And we know that this gave us this power series n equals 0 to infinity of negative 1 x to the 2n power. So we're going to use that to integrate. So we're going to have f of x is going to be the integral of 1 over 1 plus x squared dx. Because when we integrate that, we know we get arctangent. So using this in terms of our power series, I keep forgetting to put that squared on the inside. I apologize for that. That's going to be the same as integrating which is really just a power rule, because remember that we're integrating with respect to x, so the n's don't enter into it at all. So let's go ahead and write this out. So we are going to have the integral of 1 minus x squared plus x to the 4th minus x to the 6th plus, and going on like that, dx. That's going to give us these terms when we integrate it. Now I'm going to be a stickler here since this is an indefinite integral and the terms go on forever. I'm going to put our constant of integration in the front. We're going to ignore it after a while, but I just don't want you to forget that it's there. So we have x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7th over 7, and on and on. So I just use the power rule on these terms. So now I can write a general rule for this. So I'm going to have that arctangent my f of x is going to equal the summation of n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1. And now we don't have to worry about the c because it's incorporated with our sum. And we want to remember that this is valid between negative 1 and 1. Now, had we just directly integrated this summation, which we could have, we would have gotten this answer here, which was just using the power rule. So I just wanted to show you both ways. So now what we're supposed to do is, check our endpoints for the interval of convergence. And what we're going to find for both of these when we check x equals negative 1, we're going to have the summation n equals 0 to infinity of negative 1 to the n, and then we're just going to have negative 1 to the 2n plus 1, and that's all going to be over 2n plus 1. So what we're going to find is this is going to converge because we're going to compare it to a convergent alternating harmonic series, which converges of negative 1 to the n over n, and that converges. And the same is going to be true with x equals 1. We're going to have this series And we can compare that as well to the same one, because it'll have the same similarity, which converges. So our interval of convergence is going to include the endpoints, which doesn't happen often, but in this case, it does, and this is Gregory's series. So Gregory's series converges for -1 is less than or equal to x, less than or equal to 1. If we let x equals 1 and determine the resulting series called the Leibniz formula. Now this is kind of cool, because what you're going to find is, let me just write this down, I'll show you in the calculator. Oops. So if we put x equals 1 in, we have this series. This is why I love math so much, because stuff like this just blows my mind. So you can really just ignore that 1. And so it'll look like this: 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. If you put enough terms in, what is cool is this actually equals pi over 4, which makes sense because remember our original function was arctangent, and if arctangent equals 1, the angle was pi over 4. So I actually did it in a calculator. Let me show you this. This was pretty cool. So I put in the summation and I did 100 terms, and I got 0.78.787333503, and then I figured out the decimal equivalent of pi over 4, and that was pretty close, and that was only for 100 terms. So if I do even more terms, these two values would be very, very similar. So that's kind of a very interesting thing to show you how accurate these power series can be. Okay, we have one more example. And I know it looks long because it's on its own page, but it's really not. So we're going to find the power series representation for x squared over 1 minus 2x squared. And this is a trick where we're again going to start with the derivative of part of this, and we're going to build the series from that. So we are going to start with one over 1 minus 2x. And the reason why we're starting with that is that's in the form of our geometric series that we want. So we can create a series out of that, a nice series. So that's just going to be 2x to the n power, because it's in the form of a geometric series. So if we want, and there's a reason I'm going to do this because of the 2, I'm going to use it later, I can write this separately as 2 to the n, x to the n. Now, why did I start with that? Because what do you get if you take the derivative of this? So we're going to take the derivative and when we do that, we are going to get 2 over 1 minus 2x squared. And if you look at our original function, that's the pretty much the denominator there. So we're going to use that then to build our entire function from. So now I'm going to take the derivative of my series, and I can just use the power rule on this. And when I do that, I'm going to get the summation of n equals, now it's going to be 1 because when I took the derivative, I got rid of the constant term. So it's not going to start at 0 anymore. So I have my 2 to the n, I bring my power down, which is n, and then I lower my power by 1. Okay, so now I have pretty much the denominator. So if I take that and I multiply it by x squared over 2, I will have my original function, which is what I want. So before I do that, I like my geometric series to start at 0. So I am going to adjust my index here. So I can do that by setting it back to 0, but adjusting everything else so I get the correct first term. So I need to change 2 to the n to 2 to the n plus 1. And then everything has to have a plus 1 on it with the n. And then I'm back to x to the n. So check that for yourself to double check. Because if I were to put 1 in for n in this series there, my first term would be 2, which is what I want. And that's my constant. And I want that to be the 0 term. So if I do that in my new form, it's still going to be 2 if I put 0 in now instead of 1. So I want to remember that I multiplied the left side by x squared over 2. So I'm going to do the same thing on the right side. And when I do that, then I'm going to have my real function, which I want. 2's will cancel here. I'm going to have x squared over 1 minus 2x squared. So that is going to be the summation n equals 0 to infinity. Bringing the 2 in, that changes that back to 2 to the n. I have the n plus 1. And now the x is going to change power because I have x to the n times x squared. So that's going to give me x to the n plus 2. And there is my power series. And so that's how you find the power series representation using a derivative. So if you have any questions, please let me know. We're going to do some practice on this so you can see some of the tricks for yourself.